Testing, can you hear me? Testing, can you hear me? Testing, can you hear me? Okay, so this video is public now. So I'm going to be learning data structures and algorithm. I'm going to be reading the hashing chapter again. Let me just change to full screen. So in hashing, I learned about the basics and some simple hash functions. Hold on. All right. So I learned about sample hash function, the simple mod function, binning, the mid square function, and then hash function for strings. And now I'll start studying open hashing, whatever this is. And then the main thing I want to learn is the collision resolution chapter. Hopefully, I complete this chapter this stream, but we will see. While the goal of a hash function is to minimize collisions, some collisions are unavoidable in practice. Thus, hashing implementation must include some form of collision resolution policy. Resolution techniques can be broken down into two classes: open hashing, also called separate chaining, and closed hashing, also called uh, open addressing. Yes, it is confusing when open hashing means the opposite of open addressing. Separate chaining and open addressing. The difference between the two has to do whether collision are stored outside the table, open hashing, or whether the collision results are stored in one of the records on another slot in the table, closed hashing. The simplest form of open hashing defines each slot in the hash table to be the head of a linked list. All records that hash to a particular slot are placed on that slot's linked list. The following figure illustrates a hash table where each slot points to a linked list to hold the records associated with that slot. The hash function used is a simple mod function. Okay, so 100 went here and then 930 will also go here. So they're using a linked list to store values of the same hash results. Records within a slot's list can be ordered in several ways: by insertion order, by key value order, or by frequency of access order. Ordering the list by key value provides an advantage in the case of an unsuccessful search, because we know how to stop searching the list once we encounter a key that is greater than the one being searched for. If records on the list are unordered or ordered by frequency, then a successful search will need to visit every record on the list. Given a table of size m storing n records, the hash function will ideally separate the records even among the m positions in the table, yielding an average of n divided by m records for each list. Assuming that the table has more slots than there are records to be stored, we can hope few slots will contain more than one record. In the case where a list is empty or has only one record, a search requires only one access to the list. Thus, the average cost for hashing should be theta 1. However, if clustering causes many records to hash to only a few of the slots, then the cost of to access the record will be much higher because many elements on the linked list must be searched. Open hashing is most appropriate when the hash table is kept in main memory, with the list implemented by a standard in-memory linked list. Sorting an open hash table on disk in an efficient way is difficult because members of a given linked list might be stored on a different disk block on different disk blocks. This would result in multiple disk accesses when searching for a particular key value, which defeats the purpose of using hashing. There are similarities between open hashing and a bin sort. One way to view open hashing is that each record is simply placed in a bin, while multiple records may hash to the same bin. This initial binning should greatly reduce the number of records accessed by a search operation. In a similar fashion, a simple bin sort reduces the number of records in each bin to a smaller number that can be sorted in some other way. On the left is an array of numbers that are to be inserted into the hash table on the right. The hash table uses open hashing to deal with collisions. Move the records on the left to the appropriate bin on the right when using a simple mod hash function. So this goes to 3, 5, this goes to 6, this goes to 6, this goes to 9, next one goes to 1, and then this one goes to 5, and then this one goes to 3. Okay, next question. Bucket hashing stores all records directly in the hash table. Each record R with key value kr has a home position that is HKR, the slot computed by the hash function. If R is to be inserted and another record already occupies R's home position, then R will be stored at some other slot in the table. It is the business of the collision resolution policy to determine which slot that will be. Naturally, the same policy must be followed during search as during insertion, so that any record not found in the home position can be recovered by repeating the collision resolution process. One implementation for closed hashing groups, hash table slots. What? One implementation for closed hashing groups hash table slots into buckets. The M slots of the hash table are divided into B buckets, with each bucket consisting of M divided by B slots. So M slots divided into B buckets. Okay, and then there are these many slots. The hash function assigns each record to the first slot within one of the buckets. If the slot is already occupied, then the bucket slots are searched sequentially until an open slot is found. If the bucket is entirely full, then the record is stored in an overflow bucket of infinite capacity at the end of the table. All buckets share the same overflow bucket. Good implementation will use a hash function that distributes the records evenly among the buckets so that as few records as possible go into the overflow bucket. By searching for a record, the first step is to hash the key to determine which bucket should contain the record. Okay, let's see. This is an array. They divided this into 5 buckets: B0, B1, B2, B3, B4. The records in this bucket are then searched. If the desired key value is not found, and the bucket still has a free slot, then the search is complete. If the bucket is full, then it is possible that the desired record is stored in the overflow bucket. Oh, I see. So you use a hash function. Using a hash function, you will end up in one of these four bucket, which is like a subarray. And then you search within the subarray. You search within the bucket for that key. And we have an overflow bucket just in case. So take 8 mod 5 to get 3. So what are the inputs though? Okay, they're using a hash function, and the first value goes in this bucket 3, and the next value goes in bucket 0, and then the next value goes in bucket B3. Oh, 48 goes here, but it's overflowing, so it goes here. Now it's at 20, now it's at 25. 25 is overflowing. Okay, I see. Then check 1. Since we have not found it since the bucket as well, we have to look through the overflow bucket. Found it. Okay. A simple variation on bucket hashing is to hash a key value to some slot in the hash table as though bucketing were not being used. If the home position is full, then we search through the rest of the bucket to find an empty slot. If all slots in the bucket are full, then the record is assigned to the overflow bucket. The advantage of this approach is that initial collisions are reduced because any slot can be a home position rather than just the first slot in the bucket. Demonstration of alternative bucket hash for an array of size 10 storing 5 buckets, each 2 slots in size. The alternating gray and white cells indicate the buckets. Since there are 10 slots, we take 31 mod 10 to get 1. Put this in slot 1, which is in bucket 0. Now insert a record with key value 21. 21 is already used. There's a collision. So we search for the next free slot in bucket 0. Okay, so it's not necessary at the start of the bucket. It's like wherever the hash function takes it. So the hash function is not in terms of buckets, it's in terms of these indexes. It's in terms of the array indices. But if there's a collision, we search within the bucket or within the overflow bucket. 48, and then we go to 20 goes here. Okay. Bucket methods are good for implementing hash tables stored on disk because the bucket size can be set to the size of the of a disk block. Whenever such an insertion occurs, the entire bucket is read into memory. Because the entire bucket is then in memory, processing an insert or search operation requires only one disk access. Unless the bucket is full. If the bucket is full, then the overflow bucket must be retrieved from disk as well. Naturally, overflow should be kept small to minimize unnecessary disk access. Now we turn to the most commonly used form of hashing, closed hashing with no bucketing, and a closed collision resolution policy that can potentially use any slot in the hash table. Wait, closed hashing. Didn't we just, isn't bucket hashing closed hashing? Closed. This is a form of closed hashing, right? Because we are storing in the same array. Closed hashing with no bucketing and a collision resolution policy that can potentially use any slot in the hash table. During insertion, the goal of collision resolution is to find a free slot in the hash table when the home position for the record is already occupied. We can view any collision resolution method as generating a sequence of hash table slots that can potentially hold the record. The first slot in the sequence will be the home position for the key. If the home position is occupied, then the collision resolution policy goes to the next slot in the sequence. If this is occupied as well, then any other slot must be found and so on. This sequence of slot is known as probe sequence and it is generated by some probe function that we will call P. Insertion works as follows. Okay, wait. So the probe function takes in the key value and generates a sequence and it okay, and then it looks at the sequence of slots, right? Until it finds a free one. Method hash insert first checks to see if the home slot for the key is empty. Home position for E, init probe function, home key. So HT position key. Okay, we do this loop as long as the this is occupied. The hash table position is occupied. We are searching through the entire. Hold on, what's happening? I is 1, I plus plus. If k is equal to hash table position dot key, print ln. In C++, isn't the convention to use stdc out? I just noticed this. Print ln duplicates not allowed, and then we return. And position is home. The new position is the home plus we use the probe function again with inputting k and I, and then mod m. We find the new position. So we tried with so we try the normal default position and then we input 1, then we input 2, and then we input 3. I see. If the home slot is occupied, then we use the probe function pki to locate a free slot in the table. Function p has two parameters, the key k and a count I of where in the probe sequence we wish to be. That is, to get the first position in the probe sequence after the home slot for key k, we call pk1. For the next slot in the probe sequence, call pk2. Note that the probe function returns an offset from the original home position rather than a slot in the hash table. Thus, for the for loop in the hash insert is computing positions in the hash table at each iteration by adding the value returned by the probe function to the home position. The ith call to p returns the ith offset to be used. Searching in the hash table follows the same probe sequence that was followed when inserting records. This way, a record not in the home position can be recovered. Implementation for a search procedure is as follows. Implementation of the search. Oh, we are searching whether the key is the key. And if it's an empty key, then it's not there. Okay. And it's not empty key, keep incrementing I. And when you use the probe function to keep going next, until we find the thing. Until we find the value. This is within the for loop, right? Why is it not indented? Is there a way? I know this is like an open project, but I would like to edit some of these. I don't like the indentation. If k hash table position equal to key, then we return true. Both the insert and search routines assume that that at least one slot on the probe sequence of every key will be empty. Otherwise, they will continue in an infinite loop of unsuccessful searches. I mean, you have the empty key. Yeah, we are checking the empty key, right? Like if it's empty key, this is true. That if it's empty, then we go out of the loop. Wait, hold on. If we happen to be stuck in a loop of probe function, like let's say the first slot is 1, the second slot is 3, the third slot is 5, and when we use the next probe function, we go back to 1, and all of those slots are occupied. When we are searching the slot, can we fall into an infinite loop? The hash system should keep account of the number of records stored and refuse to insert into a table that has only one free slot. The simplest approach to collision resolution is to simply move down the table from the home slot until a free slot is found. This is known as linear probing. Hold on. Is it possible to get stuck in an infinite loop with this function? Probe in I. If the current slot we are looking at is not the key we are searching for, and it's not empty as well, then we keep moving, right? So we find the new position, check if new position is equal to k. If it is, then return true. If it is not, then we continue the loop. No, hey, hold on, I just realized there's no body for this for loop. So for loop I, so if the current position is not the key and it's not empty either, we go next. And we keep going next until we find the key we were searching for, or if we realize that the slot is empty, so that key doesn't exist. But the question remains: what if we end up in the what if we end up in an infinite loop? We should keep an internal counter, right? We should keep an internal counter. Actually, we should keep track of the first position. So HT position, we should keep track of the first position. And if we ever loop back to the first position, or actually no, let's say it's 135, 35, 35. If you're looping like that, you should keep an internal counter that and check if that internal counter goes more than the size of the array. So within the for loop should have a body that increments an internal counter, and if it goes above the size of the array, then we should exit the loop and return false. So linear probing means just search the next one. Okay, 9877 and then 9050 23 2037. So this already failed. The probe function says to just search the next one, which is 8. Well, that's linear probing. 9 goes here, 0. This is occupied. So if he's and try to input 9, we go back, then we input 2 2. The problem with linear probing, while linear probing is probably the first idea that comes to mind when considering collision resolution policies, it is not the only one possible. Probe function P allows us many options for how to do collision resolution. In fact, linear probing is one of the worst collision resolution methods. Main problem is illustrated by the next slideshow. If at this point we want to insert the value 3348, we would have to probe all the way to slot 2. 3348, yeah, that's true. This seems like an extreme case, but in fact, this illustrates a persistent problem. In that linear probing violates a basic goal of collision resolution method, a goal of making every free slot in the table be equally likely to get the next record. But considering the keys were inserted into the table with hash 2, a key hash to slot 0 will probe to slot 2, a key hash to slot 1 will probe to slot 2. Okay. Only keys hashed directly to slot 3 will end up in slot 3. Here are the probabilities of each. So 60, 10, 10, 10, 10, 10. In other words, clustering tends to lead to more clustering because we tend to put new records next to the old ones. The ideal behavior for collision resolution mechanism is that each empty slot in the table will have equal probability of receiving the next record. This tendency of linear probing to cluster items together is known as primary clustering. Small clusters tend to merge into big clusters, making the problem worse. The objection to primary clustering is that it leads to long probe sequences. The tendency in certain collision resolution methods to create clustering in sections of hash table. Okay. Improved collision resolution. How can we avoid primary clustering? One possible improvement might be to use linear probing, but to skip some slots by some constant c other than 1. This would make probe function PCI. So the ith slot in the probe sequence would be HK plus IC mod M. This way records with adjacent home positions will not follow the same probe sequence. So what do we call this? We call it linear probing by steps. So we insert to 4, then to 6, then to 8, then to 0, then to 2. Our record 3 goes to 5, 7, 9, 1. One quality of a good probe sequence is that it would cycle through all the slots in the hash table before returning to home position. Clearly, linear probing does this. Unfortunately, not all values for C will make this happen. 10 is divisible by 5. 10 is divisible by 2. But what if we choose step 3, for example? 0, 1, 2, 3, 1, 2, 3, 1, 2, 3, 9, and then 1, 2, 3. We end up at 2. 1, 2, 3, 1, 2, 3, and 1, 2, 3. Fortunately, not all the values for C will make this happen. For example, if C is equal to 2, the table contains an even slot of numbers, then any K whose home position is in an even slot will have a probe sequence that cycles through only the even slots. Likewise, the probe sequence for a key whose home position is in an odd slot will cycle through the odd slots. Thus, this combination of table size and linear probing constant effectively divides the records into two sets stored in two adjacent sections of the hash table. So long as both sections of the table contain the same number of records, this is not really important. However, just from chance, it is likely that one section will become fuller than the other, leading to more collisions and poorer performance for those records. The other sections would have fewer records and thus better performance. But the overall system performance will be degraded as the additional cost to the other side more full outweighs the improved performance of the less full side. Constant C must be relatively prime to M to generate a linear probing sequence that visits all slots on the table. M is 10, then if C is any one of 1, 3, 7, or 9, then the probe sequence will visit any slots for any key. When M is 11, any value for C between 1 and 10 generates a probe sequence that visits all slots for every key. Okay, pseudo-random probing. Consider this situation where C is equal to 2. We wish to insert a record K1 such that HK1 is equal to 3. The probe sequence for K1 is 3, 5, 7, 9, and so on. If another key K2 has home position at slot 5, then its probe sequence will be 5, 7, 9, and so on. Probe sequences of K1 and K2 are linked together in a manner that contributes to clustering. In other words, linear probing with a value of C is greater than 1 does not solve the problem of primary clustering. We like to find a probe function that does not link keys together in this way. We would prefer that the probe sequence for K1 after this first step on the sequence should not be identical to the probe sequence of K2. Instead, their probe sequences should diverge. The ideal probe function would select the next position on the probe sequence at random from among the unvisited slots. That is, the probe sequence should be a random permutation of the hash table position. Unfortunately, we cannot actually select the next position in the probe sequence at random because we would not be able to duplicate the same probe sequence when searching for the key. However, we can do something similar called pseudo-random probing. I mean, in random functions, they have seeds, right? Like if you input a seed, it generates the same random sequence. So we can use the seed to get the same thing back. In pseudo-random probing, the ith slot in the probe sequence is hk plus ri mod m, where ri is in the ith value in the random permutation of the numbers from 1 to m minus 1. All inserts and searches must use the same sequence of random numbers. The probe function would be pki permutation I, where permutation is an array of length m that stores a value of 0 in position permutation 0. Stores a random permutation of value 1 to m minus 1 in slots 1 to m minus 1. Let's see an example. So 10. So we chose a random permutation. Insert a record 157, 273. Set a record with key value 17. However, we have a collision. So you go to 7. Wait, what? 7, 7. Shouldn't it be 2? So now we look in the permutation array for the first value at position permutation 1. At that value to the home slot index, which is 7, to get a value of 10 modulus 10. One three seven. Get a home, which is 3, to get a value of 6. Insert a record with key value 110. Fortunately, there's already a value in slot 0. We now look in the permutation array for the value at position permutation 1. Add that value to the home slot index, which is 0, to get a value of 3. I actually don't understand what's happening. 7, 3, 4. Of course, any permutation is possible, even one that gives us a bad probe sequence, which is the same as we would get for linear probing, but this would almost never happen in practice. I need to understand how they're doing this. Here's a permutation. Insert a record with key value 157. We inserted 157, 237, and this one is a collision 70. So we look in the permutation array for the value at position permutation 1. So we're looking at 3, but why 1 though? The probe function would be pki is equal to permutation I, where permutation is the length of is an array of length m that stores a value of 0 in position permutation 0 and stores a random permutation of values from 1 to m minus 1 and slots 1 to m minus 1. So this 0 is always, the first one is always 0. Why are they looking at 1 here? Oh, yeah, in the for loop, the I starts with 1 and then 2. Yeah. Starts with 1 and then 2 and then 3 and then 4. Yeah. So perm 1. Okay, so this is set to 0 and all of this is randomized. So we look at perm 1 and then add it to 7 and then find a modulus to that. Okay. Next is 3. So we look at the first one. Since there's a collision resolution, in the for loop, it will look at the first position which is 3. 3 plus 3 is 6, so it goes to position 6. Next is 0. Fortunately, there's already a value in 0. So we look at 1, which is 3. We get 0 again. Permutation perm, add that value to get a value of 3. Hold on. Insert a record with key value 110. We add 3. So we add 3 first. 3 is occupied. Then we get rid of. Do we add 7 on top of 3 or do we add 7 to 110? No, I think we add 7 to 110. Okay, so add 7 to 110 and then mod that. We get this. This is occupied as well. Add 6 to 110, but that is occupied as well. Add 1 to 110, we get this position. Alright, I understand. First, recall what happens with linear probing by step 2. Say that one record hashes to slot 4 and another hashes to slot 6. Consider the probe sequence extending out of slot 4. It would visit 6, then 8, then 0, then 2. The probe sequence extending out of slot 6 visits 8, then 0, then 2, then 4. In other words, one of two probe sequence join, they move together, leading to a form of clustering. Contrast, consider what happens when pseudo-random probing in pseudo-random probing. Consider a record that hashes to slot 3 and another that hashes to slot 6. The probe sequence extending out to slot 3 first goes to 6, then to 4, then to 7. However, the probe sequence extending out of slot 6 first goes to slot 9, then 7, then 0. So you can see the two trails where they might meet occasionally do not follow along together. Another probe function that eliminates primary clustering is called quadratic probing. Here the probe function is some quadratic formula. So where C for some choice of constant C1, C2, and C3. Simplest variation is pki equal to I square. C1 is 1, C2 and C3 are 0. The ith value in the probe sequence would be hk plus I square mod m. There is one problem with quadratic probing. It's the probe sequence typically will not visit all slots in the hash table. Fortunately, quadratic probing has a disadvantage. Okay. Using the I square, think of any number, square it, the result will end in 0, 1, 4, 5, 6, or 9. Thus, either only these slots, thus these are the only slots that can be reached by the probe sequence for a key value that hashes to slot 0. For many hash table sizes, this probe function will cycle through a relatively small number of slots. If all slots on that cycle happen to be full, this means that the record cannot be inserted at all. The right combination of probe function and table size will visit many slots on the table, particularly if the hash table size is a prime number and the probe function is I squared, then at least half of the slots on the table will be visited. If the hash table size is a power of 2, then the probe function is I squared plus I divided by 2. Then every slot in the table will be visited by the probe function. Both pseudo-random probing and quadratic probing eliminate primary clustering, which is the name given to the situation when keys share substantial segments of the probe sequence. Two keys hash to the same home position. However, then they will always follow the same probe sequence for every collision resolution method we have seen so far. The probe sequences generated by pseudo-random and quadratic probing are entirely a function of the home position, not the original key value. This is because P ignores its input parameter K for these collision resolution methods. The hash function generates a cluster at a particular home position, then the cluster remains under pseudo-random and quadratic probing. This problem is called secondary clustering. The tendency in certain collision resolution methods to create clustering in sections of hash table. Primary clustering is caused by cluster of keys that don't necessarily hash to the same slot, but which follows significant portions of the same probe sequence during collision resolution. Secondary clustering results from the keys hashing to the same slots of the table. And so a collision resolution method that is not affected by key value must use the same probe sequence for all such keys. The problem can be resolved by double hashing since its probe sequence is determined in part by the second hash function. It's not clear what the difference is. Cluster of keys that don't necessarily hash to the same slot but which follow significant portions of the same probe sequence. In secondary clustering, keys hash to the same slot. If for quadratic, I can understand. For pseudo-random, I don't understand. To avoid secondary clustering, we need to have probe sequence make use of the original key value in its decision making process. A simple technique for doing this is to return to linear probing by a constant such step factor for the probe function, but to have that constant be determined by a second hash function h2. Thus, the probe sequence would be a form of pki I times h2. This method is called double hashing. There are important restrictions on H2. More importantly, the value returned by H2 must never be 0 or M, because that will immediately lead to an infinite loop, such as the probe sequence makes no progress. However, a good implementation of hashing should also ensure that all of the probe sequence constants are relatively prime to the table size M. For example, if the hash table size were 100 and the step size for linear probing or 50, then there would be only one slot on the probe sequence. If instead the hash table size is 101, then any step size less than 101 will visit every slot in the table. This can be achieved easily. One way to select M to be One way is to select M to be a prime number and have H2 return a value in the range between 1 and M minus 1. You can do this by using a secondary hash function. An alternative is to set M is equal to the power of n for some value M. Have H2 return an odd value between 1 and 2 to the power of M. You can get that result with this secondary hash function. Okay. Okay, I need more practice with this secondary double hashing thing. Secondary hash function, k over m over 2 times 2 plus 1 might seem rather mysterious, so let's break it down. This is being used in the context of two facts. We want the function to return an odd value that is less than m hash table size, and we are using a hash table of size m to the power of 2 to the power of m. Which means that taking the mod of size m is using the bottom m bits of the key value. Since h2 is multiplying something by 2 and adding 1, we can guarantee that it is an odd number. Now x mod m over by 2 times 2 plus 1 must be in the range 1 and m minus 1. Yeah, we are modding it, so it will be in the range 1. So this part will be in the range of 0 to m minus 2, but then we are multiplying it by 2 and adding 1. Last piece of the puzzle is the first part, k divided by m. It is not strictly necessary, but remember that since the table size is 2 to the power of m, this is the same as shifting the key value right by m bits. In other words, we are not using the bottom m bits to decide the second hash value function, which is essentially a good thing if we use the bottom m bits to decide on the first hash function value. In other words, we really do not want the value of the step size used by the linear probing to be fixed to the slot in the hash table that we choose. So we are using the next m bits of the key value instead. Now that this would only be a good idea if we have these in a large enough key range, that is. We want plenty of use of those second m bits in the key range. Okay, I'll just go next. Hash analysis. How efficient is hashing? You can measure hashing performance in terms of the number of record access required when performing an operation. The primary operation of concern is insertion, deletion, and search. It is useful to distinguish between successful and unsuccessful searches before a record can be deleted. Uh, Before a record can be deleted, it must be found. Thus, the number of accesses required to delete a record is equivalent to the number required to successfully search for it. To insert a record, an empty slot along the record's probe sequence must be found. This is equivalent to an unsuccessful search for the record. Wait a minute. When we are deleting a record, it's enclosed hashing. Then there will be empty key in that position, right? But then when we are searching it, we will come through the empty key before without searching the keys ahead. I think the next chapter will cover that. When the hash table is empty, the first record inserted will always find its home position free. Thus, it will require only one record access to find a free slot. If all records are stored in their home position, then successful searches will also require one record access as the table begins to fill up. The probability that a record can be inserted into its home position decreases. Record hashes to an occupied slot, then the collision resolution policy must locate another slot in which to store it. Finding records not stored in their home position also requires additional record accesses as the record is searched for along its probe sequence. As the table fills up, more and more records are likely to be located even further from the home position. From this discussion, we see that the expected cost of hashing is a function of how full the table is. Define the load factor for the table as alpha is equal to n by m, where n is the number of records currently in the table. Probability, wait, what? An estimate of the expected cost for insertion can be derived analytically as a function of alpha. In the case where we assume that the probe sequence follows a random permutation of slots in the hash table. N is the number of records currently in the table and M is the table size. Assuming that every slot in the table has equal probability of being in the home slot, for the next record, the probability of finding the home position occupied is alpha. Okay. The probability of finding both home position occupied and the next slot on the probe sequence occupied is n times n minus 1. N divided by m and times n minus 1 divided by m minus 1. The probability of I collisions is this. N and m are large. This is approximately equal. This is approximately n over m to the power of I. This is the upper limit, right? N by m to the power of I. The expected number of probes is 1 plus the sum over I greater than or equal to 1 of the probability of I collisions, which is approximately 1 plus the sum of this. Why are we adding 1? The expected number of probes is 1 plus the sum over I of the probability of I collisions. The probability of I collisions is this. So the expected number of probes is 1 plus this. Or we need to count the first probe as well. Like even if there are collisions the first time, collision, and then we find a slot. For finding the last slot, there must be a last probe sequence, right? So I collision and then a successful free slot. So I collision, so I probes, and then one more probe at the end. Okay, so this I understood. Cost for a successful search has the same cost as originally inserting data code. However, the expected value for insertion cost depends on the value of alpha, not at the time of deletion, but rather of the original insertion. We can derive an estimate of this cost by integrating from 0 to the current value of alpha, yielding 1 over alpha log E1 over 1 over alpha, 1 minus alpha. It's important to realize that this equation represents the expected cost for operations when using the unrealistic assumption that the probe sequence is based on random permutation of the slots in the hash table. We thereby avoid all the expense that results from a less than perfect collision resolution policy. So, plot showing the growth rate cost for insertion and deletion into the hash table as the load factor increases. So these two are insertion and these two are record and deletion. Figure 1.8.1 shows how the expected number of record access grows as alpha grows. The horizontal axis is the value for alpha. Vertical axis is the expected number of accesses to the hash table. Solid lines show cost for random probing, while dashed lines shows the cost for linear probing. Random probing, linear probing. These two are insert and these two are delete. The two leftmost lines shows the cost for insertion and the two rightmost lines shows the cost for deletion. Equivalently successful search. Okay, now next is the deletion. In deleting a record from the hash table, there are two important considerations. Deleting a record must not hinder later searches. In other words, the search process must still pass through the newly empty slot to reach records whose probe sequence passed through the slot. Oh, I mean, we can have a marker, right? Right, there was a slot. This slot was previously filled, but now it's empty. We can have a marker saying that this is not the end of the sequence. We do not want to make positions on the hash table unusable because of deletion. The freed slot should be available for future insertion. Both of these problems can be resolved by placing a special mark in place of the deleted record called a tombstone. Tombstone indicates that a record once occupied the slot but does so no longer. A tombstone is encountered when searching along a probe sequence. The search procedure continues with the search. When a tombstone is encountered during insertion, the slot can be used to store the new record. However, to avoid inserting duplicate keys, it will be necessary for the search procedure to follow the probe sequence until a truly empty position has been found. Simply to verify a duplicate is not in the table. However, the new record would actually be inserted into the slot of the first tombstone encountered. Alright. If we are deleting at the end, do we put a tombstone at the end or do we make it empty key? 5, 26, collision, 25. Now we delete this tombstone, delete 5. Now insert 97, which has a slot of 7. Find it contains a tombstone, so we can insert there. But the thing is, after a very long time, Wouldn't the entire table be like either values or tombstone? After a series of intermix, insertion, and deletion, some slots will contain tombstone. This beyond where it could be if the tombstone did not exist. Typical database application will first load a collection of records into a hash table and then progress to a phase intermix, insertion, and deletion. After the table is loaded with the initial collection of records, the first few deletion will lengthen the average probe sequence distance per record. Over time, the average distance will reach an equilibrium point because insertion will tend to decrease the average distance by filling in the tombstone slots. Do a local reorganization upon deletion to try to shorten the average path length. For example, after deleting a key, continue to follow the probe sequence of that key and swap the records further down the probe sequence into the slot of the recently deleted record. Periodically rehash the table by reinserting all the records into the new hash table. Not only this will remove the tombstone, but it will also provide an opportunity to place the most frequently accessed records into their home positions. All right. Oh, summary. Okay, I will end the stream here. Next time, I'm gonna skip memory management and go straight to indexing. Memory management, chapter 11, and file processing is, I will keep that to the end. Right, I will end the stream here then. And I'll see you guys next time. Bye.